teach anything new today, but I just want to talk. So I will say a little bit about where do you go from here if you like programming, if you like numerical programming, and that is one advantage of Python, which I tell in the beginning of the class, which I hope you agree now, that programming time in large projects. Now you are doing small projects, but that too you can see if you wrote in C, it would take you something like 5 times more time. You agree with that? In especially well, large projects also it matters. Now NASA has made a rule that they are big projects, of course they do bigger projects. All the space missions are driven mostly by well, not mostly, the computing is a major part. So they have large codes. So to design a spacecraft, there are aerodynamic issues, there is a trajectory issues, huge simulations are done. Our ISRO also, ISRO has huge simulations, and NASA made a they have understanding now that they will do the prototyping in Python. You understand what is prototype? So before you make a big aeroplane, you want to make a small aeroplane, right? Because if you design a big aeroplane, then you make one, you spend maybe a billion, well, from 100 crore rupees, or suddenly you find that doesn't work. So it's waste of money and manpower. So one thing is to make a small prototype. So it won't be running on a big computers, but it will run on a small computer. In fact, your PC, and it works, then you can design a bigger code. So these are what done for Python. So Python is definitely good thing to learn. It will help you, and but use it. If you don't use it, you will forget it. So that's one reason I didn't give many exercises which I should have had, but you can use it for your courses like quantum mechanics. Now you can program to solve Schrodinger equation. You don't have to believe what is there in the book. Sometimes what is there in the book is wrong, no? I mean, including my own book. I find that what I wrote was, I just sketched it, but when you really plot it, you find that the depth of the potential well is not so much, it is tiny, you know. So you can see those plots will be better. Electrodynamics, once you visualize those electric field, you get a better field. Plotting is very useful. So there is one problem, I am not sure which I gave in the last semester. The 8 charges sitting on the corner of a cube. So the equilibrium point is the middle, the center. But what is the potential? Anyone remembers? Is quartic order, not x squared, and that I could do it on a computer much easier rather than doing Taylor series. So there is one thing which I didn't do much, SymPy. SymPy is very powerful, and so a lot of Jackson work which you will do maybe already doing right now or next semester, right? J.D. Jackson book, the electrodynamics one. So you can do with SymPy. It requires bit of, so all these things require patience. Okay, now computing has put me patient. I was not so patient. It brings you, I mean, you have to get the code working, and that requires focus and patience. This is maybe just write this word. Focus you require and patience. Without this, you can't be a good programmer. So most of the time, I am frustrated. You know, it doesn't work. No, you have to say, well, you take a break, then you come back to the code again. Okay, so you have to have these qualities. So, so this is about general programming. So let me just write few things for programming. I have written few tips. In fact, there are books written on it. Or in internet you will find how to write good programs. There are Bible written on those stuff, and they are useful. So, I am just writing some condensed version of those things in one liners, and some of it hopefully you are practicing yourself right now. I kept mentioning it in the in between, but let me just write it. This is the last class. So, first is think of algorithms first. How to solve the problem. So, suppose you want to solve Schrodinger's equation. So, which scheme should I use? What is the problem? So, is it a particle in some conical box or square box? So, you think of the problem, do not start away right away start coding. So, think of the problem first. So, what algorithm, what time stepping I should choose, and keep it simple first. So, one thing which I have written is the first code should be simple code, which works. So, we have a big code and we use first Euler scheme, for it is easier to debug the code. So, I have some exact relations which some of you I asked them to energy conservation, that should work to 1% accuracy. We would demand more for professional code, it should be better, and so we keep the code simple. First I need to diagnose if there is an error. So, keep the code simple. This is what I had said. Remember what I said about this? What is the full form of this? Keep it simple, stupid. Then after this algorithm, you should make a pseudocode. Python is in fact very close to what you write in English, but do not worry about arrays and arrays syntax, just write a pseudocode. It is not a code, but in English you have to loop n times, within a loop I will do this. So, this is important. Okay. Now, I think before, because there will be errors if you just write without thinking, and your code will be bad code if you do not think about it in English or in Hindi also or in Tamil, you can lose. So, you have to think clearly. Programming is important. In fact, one thing I do find, let me just be slightly frank, people are not thinking clearly. Now, I find it more common, your thought patterns are not clear thoughts. It is a global phenomenon, that is my perception. I also probably do not think very clearly, but you should think clearly. I give the example of Einstein theory, that is one of the simplest theory one can start, when the assumptions are so simple. Anybody, if you tell a common man saying all physics are same for everybody, of course it is same, but what to do after that? So, I think it is important to think simple, and that is why I am quite against the culture where you are thinking very complicated n dimensional space, and then there is something and something and something which I do not know name because it will hurt some people, but it is just you are thinking complicated and it is incorrect most of the time. Okay. So, we should, so programming is very critical. If you can't think simple, your code will not work. That is my code is too complicated, it will work sometime, but it will not work some other times. So, you have to keep simple, that is very important for coding. One thing I did not emphasize, comment the code. I am not a good commenter actually. This is something which is I do not have my good practice myself, but commenting is important. I am in hurry, so we do not comment it, but next time I come back to the code I have to struggle, what did I write myself, forget about that. So, when you write large codes you should comment. So, code you submit, I would like to see at least some comments, okay, at the top, what is the code supposed to do, and there are standards at the top we have to write, I mean author's name, some licensing scheme. So, I can show you, well I do not have my code here, well I mean I will not plug it in, but I can send you one file what is there at the top, and for every function it is written what the function is supposed to do, what do the input parameters mean, what is the output of the function. So, all that is there is the standard ways to do it, which people have made it some kind of practice. Actually, it is a common language, so people accept that this is what you will have in your code. Okay. Then code slowly. So, this is important. There is no prize for coding in 10 minutes. I mean, it is not like Rubik's cube. You have to code slowly. Okay. Then code in pieces. There is something I think some students are struggling. So, you may want the whole code to work, but it never happens. Whole code never works, but part of the code will work. So, I can give the example. So, Poisson solver for people who are doing incompressible fluid flows, right. So, remember I had so we compute pressure by Poisson solver is divergence of. So, people who are doing the project, they know that this is the important part, but fortunately Rishabh has done this part which works. So, of course, works does not mean that you can just plug it in. You have to make sure that your input parameters are same as the parameter to be used by that package. So, if this code works, then you know at least one part is working. So, you do not make the building all together, you make the first floor first, then second floor. So, it is a design which people use all the time. So, you make pieces which work and then combine it. Okay. So, it is very critical. So, if you are writing this big code and it is not working because your pieces are not working, and debugging is easy if each piece by piece you try to solve the problem. And it looks so simple, but it is very critical. When it comes to practice, we do not adopt it. So, why functions are useful? Because each function can be tested. You put in the value argument and you should get an output. If it does not work, then it does not work. You have to debug that code, that function. So, it is important to code in pieces and code with confidence. And with passion. Okay. No, you can't do half-heartedly. Half-heartedly it won't work. So, you should do with nice code. You should be proud of your code. Okay. And after this is done, so first code should be simple code. First get a working code. It could be simple in the sense it may not be efficient code, it may take longer time, Euler scheme is not taking long time, but you test a small problem with this code which is not efficient. After that you make the code efficient. After the code works, you should make it efficient. So, now efficiency means now there are again techniques. So, you have to find which part of the code takes maximum time. Okay. There are tools now which can tell you which code takes longest. So, they are called profiler. This is, so there are profilers which will profile the code, saying this function 80% of time, this function takes 20% time, this function takes 10% time, this function is basically just once, it executes only once. Most of the time you will have loops, 10,000 times loop. So, something you call once, it does not have to be efficient, you do not have to spend long days to make that code which is used only once in the code. So, do not worry about that part. The one which is long, which takes longest in the code, that part should be made efficient. The profiler will tell you this code is taking long time. You can sometimes you can time yourself. This function is taking longest time, and you do it. For this code, incompressible solver, the biggest part is Poisson solver, which will take longest time, which we know from also just computation of order of complexity. Okay, Poisson solver is the longest, it takes longest time. Okay. So, why I was doing order n cube, all that stuff, that is useful. So, which is taking longer time, and that's what you should focus on optimizing. Rest part you don't need to optimize, at least in the first level. And we would like things like a library which is functions which are used more often, that should be made a library, like sine function, you know, it's a library of Python. So similarly, Poisson solver could be a library of Python. If not Python library, it's your library. So something which you use more often, you make a library, which Python allows you, and you have to do it. Now this is, I mean, all this practice is for any language. It is not for Python. It's a general programming practice. But I do want to make a remark that Python is not an efficient language. By language itself, it is not efficient. The reason why it is not efficient is, why is it not efficient? Huh? Somebody said it, right? It's an interpreted language. So interpreted. So what is interpreted? So we say first in one, you put x equal to 5, then into, then I say x star x, print x star x, you know. So I get the answer in one shot. It's like our mind, when I listen to you, I try to understand word by word or sentence by sentence. Okay. So it is live execution. So it executes this first, then this, then this. So now, I mean, how does the computer first execute this? So it converts this English language, or rather semi-English language, into binary code, zeros and ones. It has to be zeros and ones, and that zeros and ones are executed in this transistors. So here there is a binary for this, then there is a binary for this, and there is a binary for that, and so on. So every line there is a binary executed. Now if I do one at a time, then suppose somebody says you build one room, then another room, then another room. So you will start building rooms in the lawn, you know, in a haphazard manner. So you don't do the best design. However, if I write all of it in one shot in C programming language, from line 1 to line 100 is one code, and the program is compiled. So the C programming language, we compile it. So the compiler compiles this code, and that makes a executable, one executable, not like line by line executable. So this one binary is made for C of the whole package. Now these compilers are very smart, and they can make efficient codes. Because suppose somebody says in this lawn I have to make a 4-story building, you know, then you already know how to make it. So a similar idea, that it makes a optimized code. In fact, there are lot of smart people are working on this even now. In fact, the programming is evolving. The new programming languages are being created, or the old ones are being optimized for different hardwares. You know, no new hardware comes, and those poor fellows have to go back and write object codes, how to convert, how to run things on this new compiler, new processors. Every time new processor comes, you will get a new version of the compiler. And so it is very important to know one of these languages, compiler language. Okay. So this is not efficient, even though coding is faster, but execution is slower in Python. In fact, this could be 100 times slower. Than C or Fortran. So it is, coding time is faster, but execution time is slower. Now, but I must also say that right now, especially in the West, so you have the trade-off. Trade-off is whether good programmer will spend time, or I will let the program run for longer time. If it is not efficient, then you have to run it for longer time. Now each of them costs money. The computer will cost money, as the program will cost money. So So, good programmer costs money. Good programmer will cost, even in India good programmers are very rare. Well, I mean that I would rare mean does not mean 1% in the whole world, but there are good programmer is not easy to get. Okay. So, so basically you have to make a trade off, but you must, I mean Python. Okay, so what is done right now is that you write this Python library, Python code, but the ones which take longer time is written in C, or you would look for a library which somebody has written in C and you call that. And we did not do in this course, but you can Python can call Fortran libraries, C libraries and do it, Java libraries. So, Python is that way is a really, Python is like a snake which is slow moving, but it can eat anything, that is what it does. It really can eat anything, it can execute anything. So, that is the advantage of this. So, but my strong suggestion is that you should pick up another language, if you want to program. So, I recommend C++. If you believe that you have a good decent judgment, then C++ is a language. The advantage of C++ is that you can design big codes. So, as I said, you have to make these functions separate functions for each thing and then combine them. Now, if you work with Fortran, then combining these separate functions is not easy. So, the present, so you know what is object oriented language? How many of you done? Well, he knows this one, but how many people speak? Okay. So, what is advantage of object oriented languages? Okay, Rishabh, you have to.
Really big codes.
Okay, how? Why?
I mean, you can define objects for different purposes and then call these objects.
Okay, good. But I think, okay. So, by the way, most programming language allow, in fact everybody allows structures. So, array is in structure. So, you do not want to work with all these numbers. Array has certain advantages. You can how to access them. If they are more complicated data structures, like IIT Folds Institute will be built as a data structure. The student, there is a faculty, there is a staff, and there is a infrastructure. So all this stuff are there. So it is a data structure. So which is allowed in Fortran, but C++ allows functions to work on these objects, and that is part of the object. So what to do with the data is also can be packaged nicely in C++. So C++ this thing is, the object is complete. So within the object we have data as well as what to do with the data. So we have certain basis function, or we can write a library for which is self contained. You can call those data as well as print the data, for example. So for print the data, it will be part of the object, or do FFT of the data is part of the object. So all that can be done, and that's how C++ makes this each person independent, and then you can combine them, and that is the advantage of C++. Java also has that feature, but Java is a slow language. In fact, nobody, as far as I know, works with scientific computing with Java. Okay, it's slow. So I mean, but of course, a lot of people use Fortran. So there will be strong force for Fortran, and we also struggle sometimes that we have to. There are things written in Fortran, and you have to understand it, you have to use it. But I think the new thing is Python is going to wrap it up. So this is a new thing is called Python acts as a wrapper. So basically it's a so there is a code, and Python will not know what is inside, but it worries about argument to send and the result to come out. So that is a common practice, well, not common yet, but that is a very upcoming trend in computing, that you use languages like this, and then each piece you can call, manipulate and do. Okay, so all this about, in fact, how to use the code programming. Okay, but it turns out the programs or the problems you can solve with the sequential code, the one which you write, is tiny. So all the code right now you written, it runs on a single core. So you might have heard this quad core machine, right? So like my laptop has 2 cores, but my Python code will run only in one of them. Okay. But suppose I want to use both of them, or there are now machines which come with 10 cores. I mean, it's like Ravan, this 10 heads. But now you have to get all the 10 heads to work together. Well, in Ravan head, well, so all of them supposed to work together and not kill each other. So you have to make them work together and achieve the task in 1/10 the time. So that is called parallel programming. So some, let's see, 30 years back, well, so computers, the digital computer came first in 1950s. Okay, and digital first one was really with radio bulbs. You have not even seen that, those bulbs, triode. As the semiconductors were started being used, the chips came much later. But people were after making more and more efficient chips. Okay, so the big name was Cray. Cray was the company which was into making processor faster and faster. But then we reached a limit. Now this is simple quantum physics. So what is the maximum clock speed one has achieved so far is 5 gigahertz. I think I am not, actually 4 is what I have heard about, but let us say 5 gigahertz. So every computer has a clock speed, no? The electronics runs with a common clock. Okay? It's like heart of the computer, and it's synchronized. But somebody say, why 5? Why not 50? It turns out that quantum interference starts playing. So this, I am not expert of this, but the quantum level phenomena starts disturbing the computation. So you can't go above 5 gigahertz. And how many transistors can you pack? So now these are electronic objects. So the distance between 2 transistors, it can't go below angstrom, right? I mean something like 10 angstrom. If you go closer than that, then there will be all these wave functions will start colliding and overlapping. So there is a limit on how much can you pack, and that puts a constraint on how much, well, more neurons you put in the brain, you are supposed to be smarter. So that is what, so you put more and more transistor and you are supposed to be making it more powerful, but the limit was reached and these chips can't be faster than that. People are still working, they are trying to pack more and more. So this is called 14 nanometer technology. This is, you might have heard, these are the buzzwords, but you should know these words if you want to do computing. So so these are the dies, so that many nanometer, I don't fully know, I mean, but these are the, so it means packing more and more. Now, so once you say, well, I have this chip which works only, gives you this particular performance. So now remember how much gigaflops can a chip do right now, one processor? I gave these numbers. Anyone? So one core presently gives 20 gigaflop, and that is easy to see because so it can do 8 operations per second. Okay, so 2.5 gigahertz is typical thing, 2.5 into 8 is 20. Okay. So, that many operations can you do per second. So, each has a limited number of computing power, but then you can combine them together and make us the supercomputer. Now, presently I did mention in the class there are 1 million cores have been assembled. Okay. So, that 1 million cores have been, so there are ways to assemble them, and it guzzles lot of power, like full of Kanpur power this one supercomputer will take, and but it can do something like 10 power 50 times 10 power 15 floating point operations per second, okay, 50 petaflop. Okay. But now of course the challenge is how to use this machine, how to write a program which will work on the whole machine, and nobody has been able to run on the whole machine. We ran a code, well we ran on one, not this machine, but we ran a code on 196,000 processors. Okay, to be precise, this many cores. This is all of Cray XMP, no sorry, Cray XC40. So, we ran, so this our code runs on the full machine. So, it required us to work for 10 years, so we would optimize each part, because it is really a challenge that everything works together. Okay. So, how to write these codes, it takes time, and also you need to learn new functions which will make these communications possible across nodes. Okay. So, this is a new paradigm, okay, I mean which I did not touch it at all, but this we do, I teach this course, I taught last year, but this is called parallel programming, you have to, it is not difficult, but some of it you can learn yourself, but if you want to do serious computing in any field, astrophysics, quantum physics, you have to learn this parallel programming. The reason is obvious, no, because single core you can do only limited number of limited power. This I told you, this is like, I mean you can put 10 cores, that will be 100 gigaflop, 200 gigaflop. Now you want to solve problem, simulate the whole earth, the climate of the whole earth, and the amount of grid which we want to put is in billions. So, the number of elements in the grid we packed in our code 64 billion points. And Earth we have to, you really need to put more. If you, for climate modeling, the challenge is to make a grid which will look ridiculous, but the grid cannot go 3 kilometer by 3 kilometer grid. But once you make 3 kilometer grid, you know how many data points are there in along each direction? 20,000 by 3 is 6,000 each direction, x, y, and z is the height of atmosphere, and that you would like to put something like 1000 in the height. Now the height is, I mean the atmosphere is around, if you leave out that ionosphere, so something like 40 kilometers. Real activity is in, let us say, 10 kilometers. So 10 kilometers by 1000 gives you 0.1 kilometer. 10 by 1000 is 0.01 kilometer, which is 10 meters. Now 10 meter is, I mean like this full room, above the room, that is 1 point. Now that is not good, because there is lot of activity happens within that box. So you want to pack even further, but that computers also are not so powerful. And then the physics of the flow is also very nonlinear, and people do not understand how to model it. So one thing is to how to code, and secondly you also have to, computer is only as smart as a programmer. So I am not the big propounder of, or rather big believer, actually I am not a propounder, but I am not a believer of this artificial intelligence, where people think that computer can rule the world. Well, why a computer? Humans want to rule the world, that is my thing, right. It is not the computer rules the world, but there are people who want to rule the world using computers. I mean it turns out that we are all dependent on it, but then we can exploit it to control. Now, so now this is one thing, but there is another thing which is coming up. Again, I wish to work on that field, but I do not have time. But you should really think about quantum computing. Okay. Now, actually, I will ask this question which I did ask in the class, which is I think very profound question, that in a hydrogen atom, electron follows certain law and computes exactly where to be, or electron is not a particle, but the behavior of the electron is computes what to do. Now, how does it compute if you believe that world is a computer? Now, we are not thinking of the world, but I am just thinking of electron only. Now, how much resources does it have, a single electron? How many memory does it have? How much computing power does it have? But it is precisely able to compute what it should do. Now, when I compute, suppose it has, let us say it has memory and the computing power like a supercomputer, but then I know every algorithm has an error, right. This part you understood in the class, that whatever X scheme you use, there will be error unless you do symbolic computing. But this trajectory computing, this is doing some trajectory or rather wave function evolution, and wave function evolution is exact. Now, how can it be exact if it is a classical computation, or even quantum computation the way we are thinking? So, it is computing, but I can't really understand what it is doing. But if you think, in fact, there are all these big stouts who think that, like Wolfram, you heard of this Mathematica, Wolfram? There is a lot of arrogance among some people. I can say in this room, and they think this whole world is a computer. How can it be a computer if it is doing what so precisely, and no computing scheme can do so precisely? So, it is doing something, and quantum computation can give you some clues how the world behaves. In fact, that gives a different perspective. In that way, we all work with wave function psi and it computes. That is correct, but this question is also an important question. How does it know how to behave? You believe neurons is doing all my work, but how does it work? So, this is one, and the other thing now is there is a biological computer. If people are thinking of using DNA, and so you can make computers with that. Optical computer, people are trying, instead of using electrons as a pathways, but use optics. So, that also I did not. But anyway, this is important. I do think that in 10 years down the line there will be a computer, and you have to start writing the new code for that. And yeah, so the problems which is a, I did list a lot of problems in the beginning of the class, right? So some of you remember some of those problems, and maybe you thought about some new topics which are used in computation. So I will just list out few things. So any questions on this? So kind of this is what are the paradigms. This is where computing goes from first language to what you do in advanced. Well, normally people do not offer courses. There are courses for parallel computing, very often, very rarely nobody teaches in IIT. I taught it once, but I can't teach every time. So you have to learn it yourself most of the time. Okay. And there is no course on this. Well, there will be introduction, but how to use these computers, at least in IIT, I am not aware of any course. Okay, so this is in fact I tell quite often that again is a myth that you can solve with pen and paper. Now, whatever has been done whatever could be solved with pen and paper, I won't say all, but a lot of it has been done. Now with pen and paper it just becomes reasonably impossible to solve every problem. This is a big bottleneck. Now I do not mean to say that there are no smart people who can solve with pen and paper. It is possible, but very smart people have failed in able to solve those problems. So that means there is something inherently difficult in that in those problems, and which is making it problematic. Then every problem is just stuck like QCD. You know what is it, no? Quantum proof. So in fact the question, Feynman lectures are that way very nice. It tells you the problem in a simplest possible way. It says give me the mass of the neutron from the first principle. Okay. So if you think quantum mechanics can give the problem number, and try it. Assuming quarks, assume the quark mass, assume the quark mass, but then derive neutron mass. I am not saying derive the quark mass too, that is another problem, but assuming the quark mass, you try to derive QCD mass from first principle. It turns out even, so this was a one thing of QCD, and it's nobody is able to do it. The reason is the nonlinearity. Okay, it's the nonlinearity is sitting in everywhere. So the equation which comes in field theory is nonlinear, and that is what is the same nonlinearity which is there in turbulence. There is no different nonlinearity. One part has bit more complexity where the quantum mechanics plays a big role in QCD, but it's the nonlinearity which is the problem, not the quantum part. So these are, so in fact high TC superconductor is the same problem. In fact there are many problems in condensed matter physics which are again nonlinearity is a problem. So this is one example, this is called Hubbard model. So these are quantum problems, but they are strong coupling, and so very few things have exact solutions. So the only two problems which are exactly solved is Schrodinger for hydrogen atom, both classically in quantum and oscillator. Forget about particle in a box. Okay, that also is, but non-trivial problems are these two, both done classically in quantum mechanics. But there is no third problem which has been solved analytically. The helium atom is not solved analytically. Okay, as soon as you put the third object, is a 3-body problem, and 3-body problem is unsolved both classically and quantum mechanics. But unsolved does not mean, there is another issue, no? What is meant by unsolved? Does it mean you have only analytical theory that means unsolved? So one would have modified the question saying, do I understand the problem? Doesn't mean, having some, I understand somebody doesn't mean I solve somebody, you have understood that how the person behaves. Is that clear? So that is what you mean. So you understand how this turbulence problem behaves. Doesn't mean oh, this is the formula for turbulence. I think that is not very limited way of stating the problem. So given these parameters, I should be able to predict the future. If you can do it, that is understanding. I would say that is a modified way of the classical way of saying what is understanding. Okay. So that is where you are stuck, and the way to do is computation. It comes in a big way. Okay. So I think it's an important thing which I am saying it more boldly, but you have to understand that it is you have to do, and it's not solving in a simple one. You have to do parallel, and you have to collaborate. It's impossible to write those big codes alone. So you can visit the climate models. There is a big activity in so National Center for Atmospheric Research. This is a big website. Now I just want you to go and see any code which is being developed. So they have lots of code, so which does different things, So one thing is ocean model, atmospheric model, but one guy says, well, I like finite volume, so they develop finite volume. Somebody is doing spectral. and this code, each of this will, like I look at C is like WRF. So this is weather research forecast. Now look at the number of people who are working on this. So this is my just suggestion. Okay, just go and have a look. There are 100 people working on this code. Okay, 100 people. In fact, the other code, I think I forget, community climate model. I forget the name of that code. I don't use it, but there are WRF is 100 people. Now, how do 100 people combine and write a code? But single person simply can't. I mean, I understand atmosphere, but I don't understand ocean. But you have to get those two people to write in such a way that code will come and work. Now, in India, where is the effort to write those stuff? So it's critical. I mean, critical for survival to do first aid research, and that's why we don't have a climate code in India. I mean, can you imagine that? People who pride, the country which prides in software technology, there is no single code. In fact, hardly very few scientific codes. Okay, so I mean, these are things which you people are young and you should think of a new, fresh approach, and learn new tools. I mean, there is no other way. In fact, that's how you can survive. Otherwise, if you don't, I mean, if you start using Stone Age, the other guy will come with a gun and shoot you. So simple, right? So that is what is a phenomenon. We are still using Stone Age tools. Okay, good. So I'll stop.